Hi everyone, I'm Ozgur from Purdue University. I will present our paper titled Physical Side Channel Attacks Against Intermittent Devices. This is a collaboration with UC Irvine. Traditional IoT devices rely on batteries that demand regular maintenance and replacement. To address this, there has been a growing interest in intermittent devices, which harvest energy such as solar, vibration, thermal, to eliminate the need for batteries. These devices have remarkable advantages as they eliminate battery replacement costs, reduce battery waste, enable applications that are otherwise impractical, such as changing an implantable medical device's battery may require a surgery, and they provide redundancy for fault tolerance in safety critical applications due to their low maintenance. So these intermittent devices turn on when they harvest enough energy and turn off when energy is scarce. Before turning off, they perform regular checkpoints to store runtime program states such as register, stack, and global variables in non-volatile memory to ensure the forward progress in large computation tasks. Intermittent devices often have networking capabilities. When they turn on, for instance, they report sensor measurements over a low energy communication channel such as Zigbee or Bluetooth to a hub. So in this paper, we conduct a remote side channel attack targeting the energy availability of intermittent devices. Our main observation is that an adversary who learns the times an intermittent device turns on and off, which we refer to as the device's active period, can infer the energy available to the intermittent device. And such information is privacy sensitive because the device's energy availability depends on its operating environment and the user activities. So to illustrate, from an indoor solar harvesting intermittent device's energy availability, an adversary can infer the light conditions within the home, indicating whether the users are at home, watching TV, or sleeping. From a vibration harvesting device, an adversary can infer a robot's operation speed to conduct spoofing attacks when the robot is at high speed to cause maximum damage. And from a heartbeat harvesting device, an adversary can infer user activities such as sleeping or exercising. We also observe that the network packets an intermittent device transmits inevitably reveal if the device is on, since a transmitted packet implies the device is on at that time. Therefore, we consider a remote passive adversary within sniffing distance to conduct our attacks. So we conducted a feasibility study to confirm our observation. In other words, to see whether the network packet sent from an intermittent device really indicates its energy availability. So we conducted experiments in a real miniature manufacturing plant testbed. We connected a vibration harvesting intermittent device to the robot's toothed gear. This is because intermittent devices have started to be increasingly used in industrial control systems due to their ability to function in remote or inaccessible areas and their elimination of frequent battery replacements. We then ran the manufacturing plant and collected network packet sequences from our intermittent device in three different conditions: high robot speed, low robot speed, and the robot is stationary. The packet sequences illustrated in this figure show clear differences across different robot conditions, where the intermittent device sends packets at a higher frequency when it has more available energy due to the vibration from the robot's high speed, and this confirms our initial observation. However, systematically inferring privacy-sensitive information from intermittent devices in real-world IoT environments presents three main challenges. First, the adversary must distinguish the intermittent devices from the traditional devices with batteries because they usually coexist in real-world environments. To address this challenge, one could consider using the prior IoT device fingerprinting techniques, but these techniques do not consider some properties unique to intermittent devices, such as their firmware configurations, execution models, and energy storage mechanisms, failing to accurately fingerprint and identify them. Second, the adversary must identify the intermittent device's energy harvester, because the privacy-sensitive information that can be inferred is actually tightly coupled with the device's harvester. However, this is a challenging task because similar energy conditions with different harvesters may cause devices to have similar active period patterns. And lastly, the active period of an intermittent device is influenced by many user configurable factors unique to intermittent devices, such as capacitor sizes and packet transmission intervals. Thus, the adversary's energy inference algorithm must integrate these factors to accurately learn the device's active period. We address these challenges with a new side channel attack against intermittent devices. Our system models the active period of intermittent devices in a hierarchical inference framework in the offline phase and uses this framework to identify an intermittent device, its harvester, and its energy availability conditions at the online phase. Now let's take a detailed look at the key components of our system. So in the offline phase, the device property analyzer identifies the configurable intermittent device properties that are causally related to the device's active period. For this, we conduct controlled experiments to uncover the causal structure between the intermittent device's active period and its user configurable properties. For this, we apply dynamic time warping on inter-packet arrival timings to identify the intermittent device properties causally related to the device's active period. After this, grid testing runs the device with different combinations of the identified device properties in various environments, while the device is connected to different energy harvesters to collect a comprehensive timestamped packet sequence dataset. After we have this timestamped packet sequences, we then conduct active period modeling to derive our hierarchical inference framework. So given the collected timestamped packet sequences, we first pre-process them to segment them into multiple samples with window size W. We next compute the inter-packet arrival timings of the packet sequences, and then we extract time domain features from each sample. We then leverage relative mutual information to automatically select a subset for active period modeling. Lastly, we model the device's active period patterns through its inter-packet arrival timings with changing device properties, energy harvesters, and energy availability. This module outputs the hierarchical inference framework to identify an intermittent device, its harvester, and its energy availability. And then in the online phase, we first use a network sniffer to remotely collect timestamp packet sequences from the devices in a real-world environment. We then separate each device's packets based on their unique identifiers, such as their MAC addresses. And then we leverage our classification framework to continuously infer the intermittent device's energy availability. So we evaluated our attack in a real smart home and Fisher Technic manufacturing plant testbed. We use real intermittent devices with 3 different harvesters: solar, vibration, and temperature. We first collected network packets in a lab environment, as you may see in this figure, to train our models. This is because we assume the adversary does not have access to the device's real operating environment. So we train our hierarchical framework in the lab from the packet sequences collected from the lab environment, and then we use them on the real world environments. So we deployed the intermittent devices in 3 different real world environments for testing. In the first experiment, the intermittent device is connected to the solar harvester in a smart home where the light conditions change. And here the adversary aims to infer the light level, which can indicate whether the users are at home or sleeping. In the second experiment, we connected the vibration harvester to our manufacturing plant. We connect the harvester to a robot in the high bay warehouse. This robot controls the position where a workpiece is stored. So here the adversary can infer when the plant is operating the high bay warehouse and what the workpiece position is in this warehouse. And lastly, we connect the temperature harvester to the outside of an electric oven and collect network packets. Here, the adversary aims to infer the oven status, whether it's on or off. So our results show that we can identify the intermittent devices in an environment with 98% accuracy, its energy harvester with 92% accuracy, and its energy availability with 85% accuracy. In particular, the adversary infers the light level in the smart home with 80% accuracy from the solar harvesting device to learn if the user is sleeping or not at home. The oven's temperature level with 87% accuracy from the temperature harvesting device to profile the user's cooking activities, and the robot movement patterns with 88% accuracy from the vibration harvesting device to learn the time the robot is operating. We also evaluated our attacks' effectiveness under existing defenses against network analysis attacks. Particularly, there are 3 main defenses in literature: packet padding, traffic injection, and traffic reshaping. The packet padding concatenates dummy bytes to packets to confuse attacks relying on packet lengths. Since our attacks only rely on packet timings, packet padding is inherently ineffective against our attack, so we consider the other two defenses. Traffic injection introduces dummy packets to obfuscate the real network traffic in a crowd of dummy traffic. With this defense, our attack's accuracy only decreases 2.6% on average. And traffic reshaping introduces random delays between packets to confuse attacks that rely on inter-packet arrival timings, causing our attack's accuracy to decrease by 2.8%. The reason these defenses are ineffective is because the transmitted packets still indicate the device is on at that time. Therefore, they fail to hide the device's active period. Overall, our evaluation highlights the need for new countermeasures. So to conclude, we present a novel remote sidechannel attack against intermittent devices. Our attack exploits the intermittent device's active period to infer its energy availability conditions. To this aim, we design a hierarchical framework that profiles the intermittent device's active period to discover if an intermittent device is present in an environment, recognize its energy harvester, and then infer its energy availability conditions. And our evaluations with real intermittent devices show that we can infer privacy-sensitive information with high accuracy. And through this effort, we put forth an important step towards understanding the privacy implications of intermittent devices and encourage the development of new defenses against our attacks. So that's all I have for now. Thank you so much for listening.